Erik, thank you so much for coming on the podcast. I really appreciate it. Thanks for taking the time.
Oh, thank you for inviting me.
Hey, absolutely. Erik, you changed the world recently, and you gave us faster than light speed travel, at least theoretically, right? You published a paper recently where you outline the options, how we can achieve that. And it's been so long, and I had many people here on the podcast who were very, very convinced that this barrier can never be broken. So I'm really curious about your thoughts, and maybe you can help us a little bit more how you came up with this. What did you do before, and what makes you so confident that this could actually be a possibility?
I mean, I've been interested in this field for decades. Like a lot of people who get into STEM as a profession, we were all fans of science fiction in one form or another as children, and for me, it was definitely Star Trek. And I was really fascinated by the whole world that was set up, by all the series and movies and whatnot, and I really resonated with the technology that seemed to facilitate all of these things. And one that really stood out to me, that was really the physical link between this interstellar community possible was the warp drive. Otherwise, you'd be spending tens of thousands of years just trying to communicate across this vast network of civilizations. And so this seemed to be a really key point. And as I became older, it became obvious to me that someone would have to invent such a thing. And so it's been a fascination to see if something like one of these plot devices like the warp drive technology would actually be possible in the real world. And it took some time in order to build the technical acumen in order to be able to pursue that. But the desire was always there. And so what happened that say 2021 or really 2020 became the year that this paper came out for me is that I found the time to actually really delve into the topic. And we can, I guess, thank the pandemic for that, because I found myself sitting at home with a lot of free time on my hands trying to find a way to fend off cabin fever. And then this project that I really wanted to do. And so I delved into the literature to see what the status of people who had passed had been, because as your listeners may know, there is some existing literature on the concept of warp drive. You could say it kind of started seriously with Miguel Alcubierre in 1994. When he was still a graduate student, he made this Alcubierre drive, this first example of a mechanism that could transport observers like you or me, people who move primarily through time rather than space, find a way that they could move effectively through this manifold of space-time, effectively papers in the decades since then. And like you said, the literature seemed to indicate that this was, while you could create such imaginary geometries, they were not really feasible because they had all sorts of problems, namely having to do with what sort of matter and energy would be needed to source them. And so this was something that was still a problem in the literature when I looked back into the spring of last year. And I wanted to see if there were any loopholes, if there were any stones left unturned in all of the possible solutions to Einstein's relativity that would allow for both a mechanism that could transport things at arbitrary speed, including faster than the speed of light, as well as not necessarily need these exotic sources of energy and matter.
Yeah.
And so the process that I undertook to do that was essentially just start to delve into different types of geometries that would provide these properties that I wanted, and constrain down, come up with a set of rules that would narrow down that set of solutions. These other constraints like positive energy and other things. And eventually I found a sufficient set of rules that I could construct via computer simulation how one of these geometries, an example of one of these geometries, and that's what you saw in the paper last year and what's been circulated in the past few months in the media. So this is all very exciting. I don't know if I'd say I've completely changed the world yet, because there's still a lot of challenges ahead to this sort of research, but it is very exciting.
Yeah. That sounds fascinating, Erik. When you published this paper, and it's been a couple of months since then, when you would have to explain your theory to a 13-year-old, right? How would that work? Maybe we can be in that same position. How can we actually get to that point where we can travel faster than the speed of light? What is necessary, and what effect are we taking advantage of?
Well, we're taking effect of the advantage that, unlike special relativity is usually what we appeal to when we think of nothing can move faster than the speed of light. That's relativity. That's actually not quite true. In the context of special relativity, and the principle of special relativity says that two objects cannot move relative to each other at a single point faster than the speed of light. So this is a very local statement when we bring it into the context of general relativity. So because moving from special relativity, where we're all moving on this flat background space-time, Minkowski space-time, and we make that space-time in the context of general relativity dynamic and reactive to the matter and energy that lay on it, there are a few tricks that we can take advantage of. Namely that if we separate bodies, there's now no longer a principle that says that the bodies cannot move away from each other or towards each other, being at two different points, effectively faster than the speed of light. In fact, we see a phenomenon like this, we believe, in our own universe, namely this acceleration quantity, the fact that galaxies very far away from us appear to not just be moving away from us, but accelerating away from us. This is a phenomenon called inflation. There's also a period that we believe in the early universe where a much more violent form of inflation happened, where objects moved away from each other at a rate that increased exponentially with time.
Yeah.
And
some of those
other
galaxies and planets, from what I remember, they move away faster than the speed of light. So we can never catch up, right?
Right.
So we will never see that galaxy again.
Precisely, right. And by virtue of them being further apart and this acceleration sort of mounting with that increasing separation, eventually they start moving away from you faster than the speed of light, and they fall out of what's called causal contact. It means that you can't communicate with them anymore via something like a light beam. And they fall behind what we refer to as a horizon, an event horizon, of a different type than, say, you'd find around a black hole, but similar in effect, that you can no longer communicate between these two bodies. And we're essentially doing something similar with the warp drive. We're taking advantage of something that kind of looks like inflation, a much more complicated form of inflation, because it doesn't necessarily just inflate, it also contracts. And use this to our advantage in order to effectively make some motive device that propels us through this space-time. The Alcubierre metric is maybe the most intuitive form of this concept, in that when you calculate what's called the extrinsic curvature, it's the form of curvature. It essentially tells you how space is being curved in the presence of the higher dimensional space plus time manifold. But what it tells you is, for the Alcubierre metric, you have this nice picture of what almost looks like a wave, and this is what is propagated in the media very often, that you have some flat region in the center of this warp bubble, also can be referred to as a soliton because it's nice and compact in size. And in this center flat region is where you'd put a ship or some such thing. In front, on the leading edge of the bubble in the direction of travel, you have this dip in the graph that's most often circulated. And this tells you that we have a relative contraction of this extrinsic curvature. That's kind of telling you that the space is being compressed in front of the bubble. And behind, we have this peak in the extrinsic curvature, which is telling us that the space behind is relatively expanded. Now, the combination of these things kind of gives us an intuitive feel that we are kind of making the distance to our destination shorter and the distance from our origin point longer. This is it's not entirely accurate because this region of locally contracted and expanded space does not extend all the way to the destination or from the origin. But it does give us a nice intuitive feel for that you're essentially dragging yourself along by sort of pulling yourself by contracting space in front of you and renormalizing it behind you by expanding it. Now, other solutions are a bit more complicated in that, and the interpretation becomes a little less clear. But most of these solutions do have similar. All of the solutions have curvature of one form or another. The particular type of curvature that's put in this plot of this nice Alcubierre drive wave shape most of them are non-zero, but not all of them. There is one example, one well-known example called the Notatio drive, where that particular form of the curvature is zero everywhere.
Yeah. Well, and I know that was mentioned in what I read about the white paper. It would reduce the speed of travel, say, to the next star system to a few years or a few dozen years, right? Instead of, I think at current propulsion systems that we have, it would be a few hundred years, a few thousand years, right?
Well, right. Current chemical rockets, they're limited by their exhaust velocity and how much fuel you can carry, which the limit is the entire vessel is made of fuel.
Yeah.
And at that limit, you are essentially, I believe, limited to about twice the exhaust velocity, instantaneous exhaust velocity. So with current chemical rockets, we're talking about some tens of kilometers per second, which translates to tens of thousands of years to get to Proxima Centauri, which is a bit excessive. There are somewhat
there was
nearer
recently a movie about that. I think it was 3 Generations, right? I don't know if you watched that movie.
Was this with a Was this with a nuclear rocket?
Yeah, well, they had children. They had children that are born in a traveling rocket, so to speak, and they were primed and raised by themselves with no parents around. There's one parent around, but he kind of dies early. And then the idea is that they will, their grandchildren will actually be at the same age when they reach their destination. It's only about 100 years, right? It's not super long. And then the whole ship kind of falls apart until then. There's a lot of struggle, and eventually they make it. So it's a good movie, though. It's well done.
Yeah, I think I missed that one. Which one is it?
I think it's called Voyagers. The Voyagers.
The Voyagers. Okay, I'll have to look that up.
But I believe. Months ago.
Oh, really? Okay, that recent. But I believe the rocket probably used in that movie was a nuclear rocket, because their exhaust velocity is much, much higher. The energy levels able to be utilized from nuclear fuel, whether it's fission. Fusion's obviously much better. The utilization percentage is much higher. But I believe, there have been some studies to say that, say, with a nuclear fusion rocket, it may be possible to make the trip, to speed one ship up to some tens of % of the speed of light. Of course, that would take some time, and so the journey would take maybe a generation or two. Yeah. Yeah,
Freeman Dyson worked on the Orion spacecraft. He was one of the co-conspirators.
Right.
And they had supposed to have micro explosions, nuclear explosions, and that would propel them if they were controllable. Also, depending on how much material they take with them, unless they go, I don't know, close to a star and refuel. I don't know if that's so feasible. But it's at least it sounds faster. It sounds more sustainable. But it was because of the nuclear arms treaty. It never went into any testing from what we know. Right. Maybe it's hidden from us. that part of history?
Perhaps I do know that there were some tests of fission rocket systems, I believe all the way up into the early 70s, but those were also discontinued. There are some, I guess, small collections of engineers and physicists who would like to resume those tests, just because the specific propulsion of those engines is much higher than chemical rockets. But I don't know what the status of that is.
Yeah. Well, there's people who say we have these bases on Mars, and we communicate with the aliens there, and that's where we build all these rockets on the dark side of Mars, right? Well, maybe that's a little bit too much of a conspiracy. Going back to what you came up with, it generally seems so with faster than light speed travel. Initially, it all sounds relatively easy until we realize, whoa, the amount of energy that's required, and often that seems to be bigger than the sun, and that's where the discussion ends, because we don't know how to harvest even a portion of the sun properly with solar cells here, but we are really far away from harvesting the full sun power. Freeman Dyson was working on something similar. How does that work with your theory that you are suggesting?
Well, my theory is, I guess, also impractical from a total magnitude of energy viewpoint. The previous warp drive studies required, yes, on the order of solar mass magnitude energy. And I'm not just talking about the radiative pressure of the mass. I'm talking about converting every kilogram of mass in the sun into an actionable form of energy via E equals mc squared type of conversion.
A perfect conversion.
But not only was it
a perfect conversion, right?
Yes.
That has never been achieved. Yeah.
Well, only via matter-antimatter annihilations. Those are the only ones that I'm familiar with.
We don't use them so often
not only
these days.
It's a little expensive at the moment. I think some thousands of trillions of dollars per gram. It's a little out of our reach. But in any case, not only did the total magnitude of energy need to be of the order of solar masses, the sign was also what made it impractical. Not only did you need that magnitude, but you needed to make it out of some media that we don't know exists in that sort of concentration and that sort of density. We needed exotic matter, things with negative energy density of some very, astronomical size. We needed to be able to make that. We needed to be able to make it stable. There were some initial papers, I think by Fenning and Ford, they were the first ones to make the computation of the Alcubierre drive to say, okay, it may be possible that we use properties of the vacuum, use a Casimir effect in order to make naturally occurring exotic matter. We essentially make the width of this bubble so small that we get a Casimir effect, so the local energy density can, via quantum effects, become negative. But in order to make that bubble wall thin enough so that these would naturally occur, we would need to make them on the order of hundreds of Planck lengths. Planck lengths are, what is it? It's 10 to the minus 30 or so centimeters or so across. It's extraordinarily small, far beyond the distance scales that we can probe, say with the LHC. Some many orders of magnitude beyond that. But you need to make that all the way around a bubble, and say if you made the bubble interior 100 meters in radius, the total effective negative energy you'd have to make that bubble in the bubble wall would exceed the total magnitude energy in the visible universe by orders of magnitude. So it becomes extremely impractical, very much a problem. So instead of making it naturally occurring a Casimir effect to fuel this, you'd want to find some naturally occurring stable source of negative energy density, which we may have some hints of something similar to that going on with dark energy, sources of inflation that we seem to be observing in the universe, but we don't know precisely what the sourcing media looks like. But in order to make that in such high densities, in such concentrated quantities, we have no idea. It's much easier to, say, take things with positive energy density, atoms, the things that you and I are made of, and try and manipulate that to make very high density dynamic fluids in order to source such things. But before last year, we didn't really know how to make a solution that could utilize these sources and actually make a warp drive out of them. And that was sort of the impetus for me looking into literature and making the paper that we saw come out last year and get published in the early months of this year.
Just to be sure, with what you're suggesting in that paper, what is the amount of energy required just to go to Alpha Centauri?
Right. The energy question. So the energies are similar in magnitude to the old estimates, but the sign is correct now. Now we have positive energy densities. But to make something radius 100 meters go at the speed of light, we would need some tens of % of the solar mass equivalent in order to do that. So very high amounts.
20% of the sun we would need.
Yeah, say 20%. Right. Yeah. So some 5 times 10 to the 29 kilograms of material compressed into something that is 200 meters across, and that's to go the speed of light, not faster. In order to go faster, you need more energy. But then you could get to Alpha or Proxima Centauri in a little over 4 years.
Yeah. When we think of this, and we obviously in the extremely early days, and that's all theoretical. But just if we take this all the way out, so we're going to be way more efficient, and it's only going to take 1% of the sun to travel that far. And at maybe an even better speed. So we make magnitudes of improvements. I'm thinking of the early days of the internet, right? We put all this fiber under the ocean. Mm-hmm. We thought, it's not going to be enough. And then 5 years later, we realized, man, we're 100 times more efficient. So we actually put too much fiber underneath the oceans. But so I'm saying there's going to be a huge amount of efficiency gains to be made if we ever get into a practical solution. But I mean, we only have one really easy applicable source of energy in our solar system, right? It seems like still an amazing amount of energy that we have to procure. And even if we get way more efficient, interstellar travel, we're going to get rid of all the suns, right? If you take it from such a solar source, it doesn't mean that's what it's going to be. But it seems inherently very limited. So if anyone comes up with interstellar travel, it seems to be we have to create.
Right? Wouldn't we be seeing a blinking out of all the stars in our galaxy?
The stars should be going away. Yeah. That's what I'm trying to say, right? Because I mean, the equations that you make, they're right? You can't do much about it. The energy seems to be, if we are curving space just to go to the next star system, which seems to be a huge effort, then there shouldn't be a lot of stars left. If someone else in the universe sooner or later has come up with such a travel system.
Right. So I would agree that if we cannot make extreme savings in the energy efficiency of these warp drives, then if they ever become feasible, that would pose an existential threat to the rest of the galaxy. Yeah. I still have some hope that gains in efficiency can be made far beyond the 1 or 2 orders of magnitude that you just mentioned. I'm hoping that something on the order of tens of orders of magnitude can be of savings can be made in the energy density. There have been studies, again, in the context of the Alcubierre drive, the Notario drive, things that already used exotic matter in order to save energy on tens of orders of magnitude scales. So maybe bringing the energy from 10 to the 30 kilograms to 10 to the 20 kilograms, 10 to the 10 kilograms, maybe even down to the kilogram scale. Yeah. And if we're talking about a kilogram scale, then maybe we're in the realm of something like a fusion generator or even a fission generator, especially if we, say, slow ourselves down for the prototypes, which I think would be inevitable, right? You'd want something that is both smaller in diameter, so maybe you are putting something the size of a small satellite into one of these warp bubbles, and you're making it move, say, some kilometers per second in orbit. Maybe you're just having it change orbit above the Earth. Then you don't need nearly as much energy as well. Yeah. You can scale it down in that way, but you'd also need
For sure,
some
but
other
we want to
energy-saving
go to the
mechanisms
stars,
just to get
right?
there.
That's where we want to go. We want to go to the stars because otherwise we can almost go there right now. I mean, it takes a little bit of effort, but maybe, Elon brings us to Mars in 10 years from now. One of those problems that we have with traveling close to the speed of light is that time is so relative that the people inside that spacecraft have a very different perception of reality and how time goes than the people who haven't traveled. So we would never be able to return into the same time. I think depending on the speed, it could be thousands of years different when you return. Like the Earth has I always confuse who's traveled quicker, but you definitely in a hundreds of generations after you've left. I know that's only for 8-year trip to Alpha Centauri and back, and you're 10,000 years into the Earth's future. But with the warp drive, we can avoid this, and I'm curious how this works.
Right. So the twin paradox, that example from special relativity, where you have two twins, one moves away, experiences time at seemingly a slower rate because when they return, the one that went on a trip has aged relatively little compared to the one that stayed on Earth. How this changes is because they change reference frames, right? They start in the same reference frame, then one twin accelerates to something close to the speed of light, and you get all of these dilation effects. They accelerate again to return, and then they come to a standstill relative to the original twin.
But Eric, if we travel with the speed of light, then time stands still. We don't age, right? If it's not possible.
Sorry, close to the speed of light, near light speed.
Okay. Yeah.
Sorry, I was being imprecise. But in the case of the warp drive, you, if you were to recreate this twin experiment, you start off with one on Earth, one gets in a ship, the bubble forms around it, and off they go, seemingly accelerating from the viewpoint of the one on Earth. They see the ship get farther away, but within the warp bubble, the second of the twins never feels any acceleration. They do not accelerate. They do not effectively change frame of reference with respect to the original twin. So the rate of passage of time locally for both of these twins remains the same.
Because
so
space
the
is
twin
curved, right? The ship is in the same position, but the space is
the reason why they're separating while not necessarily experiencing different rates of passage of time, yes, is because of the curvature. Yeah. But so the twin that's traveling goes to Proxima Centauri. The curvature collapses so they can actually say look around, and this twin has aged. Say if they're moving at the speed of light, the drive moves at the speed of light. They've aged 4 years. They've seen 4 years go by from within the ship. Then they get back in the ship. The warp bubble accumulates, and they come back to Earth to tell everyone about what they've seen. And they come back, and it's been total, say, 8 or 9 years. But also, the original twin on Earth has also aged that same amount. So you don't necessarily have the same problem of being able to explore the universe, but never being able to tell anybody about it because your civilization is long since dead.
Yeah, that's really neat. I think it really solves a lot of practical problems on that.
I guess, although it does necessarily mean that in order to really see much of the surrounding galaxy, you really have to be able to accelerate faster than the speed of light, right? Because you're still limited by the passage of time for the people in the ship. So you really want to not just meet the speed of light, you really want to get beyond it 10, 100, 1,000 times in order to really be able to travel, say, to the galaxy center and back in a reasonable amount of time within your lifetime.
Yeah.
There's still that challenge.
What happens if we travel, say, 10,000 times the speed of light? So let's assume that's in that warp drive. That's in a future scenario. What happens to time when that person that traveled comes back to Earth? Would that still hold true that time has moved the same for both twins, or would that be a different constellation?
I mean, I think it would be effectively true, right? You can, of course, design one of these warp drives that does have the ship inside experience some acceleration. So you do have this difference in time rate of passage. But beyond that, no, they should match fairly precisely up to, I suppose, what happens during the process where the warp bubble is sort of accumulating in magnitude.
Yeah.
What would be seen by somebody outside of it as the acceleration phase as the ship moves off. And that is actually something that hasn't been done in the literature, a precise mechanism for accelerating or decelerating one of these. Although I imagine because of the very calm nature of the spacetime inside of the bubble, it would be fairly straightforward to maintain that throughout the entire process. So they wouldn't experience any acceleration, so the rate time of passage wouldn't change. But there's the question of, okay, so what happens if you are going to see a star that is moving relative to the Earth, right? You're going to have to, there's going to be effectively some dilation between your original frame of reference and your destination. So you're going to have to match that in some way. And so there'll be some effect when you're exploring whatever that star or other galaxy, whatever your destination is. There'll be whatever physics goes on during that time. And then you'll have to reverse the process and come back. So there may be some effects from matching the trajectory of your destination. But if we're just dealing with the plainest of scenarios and the two objects are sitting on a relatively flat spacetime and moving, not really moving relative to one another, you shouldn't really see that sort of impact.
What it sounds like, it's a bit like the Stargate universe. I'm a big fan of the science fiction show. And what their pseudoscience, so to speak, is, right? So they have these gates and you basically go through the event horizon. And you don't even have to move, right? So you're exactly being re-represented on the other side of the event horizon. And it's not a beaming device, it's not like Star Trek, but it's well, when I hear that, I feel like the ship is basically, it only has to move a few inches, right? Because space has moved so much around it that the ship movement doesn't really matter much anymore, right? And depending on how much how you create that warp bubble. But let's assume we can make it a gate, like literally something we have at home, like a home device. Yeah. You literally just enter the warp drive on your own, you jump into it, and you jump out on the other side, or it pushes you out. Let's say that. And we wouldn't necessarily. I mean, we can basically travel in a spacesuit, right? Because we are in it only for a few seconds, and then we come out on the other side. Do you think we can go that far?
I mean, that's kind of the general assumption that I put into my solution, and what has been done with the other solutions is that it's a very calm area inside the bubble. You're essentially in free fall, right? So like somebody out on a spacewalk, you have the sensation of floating, and even as the bubble forms around you or dissolves around you as you reach your destination, you feel virtually no sensation whatsoever as far as motion is concerned. Our typical intuition about motion really is based on acceleration or vision of things moving relative to us. You would have some sensation of seeing things move by, but you wouldn't have the sensation of acceleration. You wouldn't feel that you were being pulled or pushed or anything like that.
So there's also no radiation problem, right? A lot of people felt that with warp drives you have huge radiation issues.
Well, yeah. So there are there are problems with radiation from a couple different viewpoints. There's the Hawking radiation issue, that if you create a warp drive fast enough, you create an event horizon. You essentially isolate the inside of the bubble from the rest of the universe. And that has its own just classical physics problems in terms of how do you, if you were able to make one of these things and you have a horizon, how do you communicate with the rest of the bubble? So when you reach your destination, you can actually dissolve it and rejoin the rest of the universe and actually observe what destination you went out to go see. And that's a whole other problem. But having to do with radiation, once you create one of these event horizons, there is this concept of Hawking radiation, where if virtual particles are created on either side of the horizon, they will be out of causal contact and be unable to annihilate with one another. And so you get effectively radiation of particles that are created on your side of the event horizon, and they can impinge on you. And there have been some calculations of the radiation that would possibly result from such a horizon, and it's not good. However, I think some of these difficulties can be overcome simply by virtue of geometry of the interior region, right? The initial Alcubierre drive was very spherical in shape. The shell, the shape of the event horizon was very spherical, so everything that would appear on either side of the horizon would propagate towards the center. So the ship would, the entire volume of the interior would be radiated. It's possible that if you shape the edge of the horizon in such a way, you may be able to create regions that are radiation free.
Okay. Yeah.
So that may be one way around it. It's not necessarily omitting radiation within that calm region altogether, but it's, I think, a step in the right direction. There's another problem having to do with radiation in that you have this shell that's moving at faster than the speed of light. What happens to things it runs into? Right? There's space dust, there's comets, there's all sorts of things that it could possibly encounter on the way to its destination. What happens to those? Well, with the standard Alcubierre drive, it seems like all of these objects that impinge on the leading edge of the bubble get stuck. They get their time rate of change as they move through this high region of high curvature. Essentially, they get swept up with the bubble and they move along with it. So you have this mounting shell of energy on the leading edge of the bubble. And what happens when you then stop the bubble? If you're able to overcome this horizon problem and stop your drive at your destination, what happens to all this energy on the leading edge? Well, it seems like it gets radiated out in front of you in almost kind of some very coherent pulsed laser beam. Yeah. And so that could also be potentially very dangerous to your destination mostly. Yeah. But that might also be something that can be overcome via geometry, that you could perhaps, instead of necessarily catching everything, you could change the front end of the shell or change the geometry, not just the shape, but the actual degrees of curvature, so that instead of getting caught in the leading edge, you might be able to deflect it around. Okay. And it would essentially come out the back end of your drive relatively unimpinged on.
One thing that I immediately thought of is when we now think about them. I love how detailed you're already into this. When we think about a faster than light speed travel, someone in this universe must have done it. And that's known as kind of the Fermi paradox, which isn't really a paradox. It seems to be just a lunch note. But anyways, it's became known as this. Others must have done this, and why didn't they visit us? And maybe when you talk about the issues that there are with faster than light speed travel, is it possible that some of the things we see in the universe are kind of a pollution created by other people creating warp drives? Thinking about black holes, thinking about pulsars, quasars, all these things that we see, maybe they are just pollution where somehow the warp drive didn't work properly. Is that something that ever occurs to physicists, or this is just too much science fiction?
I think it occurs to physicists, but I also believe that there is a mantra that happens in physics, particularly in astrophysics, as they encounter new phenomena that they are unfamiliar with. They don't know. They see some gamma ray source, some repeating gamma ray source, or unrepeating, some new phenomenon that they're unfamiliar with what exactly is causing it. And I think for a lot of them, not some small part of their brain is saying, oh, maybe it's some sign of intelligent life of some advanced civilization. But then this mantra also comes into their mind, okay, it can't be aliens. I can't say it's aliens because that's perhaps that'll get I'll get branded as the person who says everything is aliens. And so they look everywhere but for a result. And so far that seems to be working out fairly well. But as we advance our own knowledge of what different phenomenon we can create via technology, like possibly this warp drive, we're confronted with questions, Fermi paradox-like questions. Do these things, can they actually exist? And if they exist, and we can create them, why hasn't everyone else? Why don't we see signs of this? In the case of the warp drive, you already mentioned one, right? Why don't we see suns blinking out because we need so much energy seemingly to make one of these? Well, maybe if these things are actually happening, there is a means of saving vast amounts of energy so you do not need so much. Maybe you only need an asteroid's worth, something like 10 to the 12 kilograms. Those are much more difficult to see, disappearing from other star systems. As far as seeing the effects of, say, the creation and acceleration and deceleration and diffusion of one of these drives, it may be that such signals are very focused. That instead of seeing some gamma ray burst, right, which radiates in many different directions, fortunately for us, with such intensity that we, even being, light years or tens of thousands of light years or millions or billions of light years away, we can pick up some few light particles, some few photons in our telescopes. It may be that these drives are very efficient in that they don't give off much in the way of excess radiation.
Yeah.
That's also possible. I'm a little less sure of that one, considering some of my recent thoughts on how one would actually accelerate one of these drives. Because not only do you need to satisfy the Einstein equations, which are what tell you, given a particular source of matter and energy, how the space-time is going to react. You also need to satisfy the general relativistic form of conservation of momentum, or referred to as conservation of stress energy, the covariant conservation of stress energy. You need to, if you're going to create something that propagates across space-time, this thing cannot just create non-trivial stress energy out of nowhere. There has to be some equal and opposite type of reaction, right, in a covariant geometric sense. And what does that look like? That might be a possible signal, but precisely what that sort of radiation or geometric disturbance, maybe there's some gravitational wave given off by one of these drives as they accelerate or decelerate. I don't know yet, but these are definitely things that I'm thinking about.
Well, what's great about the warp drive is it gives us the option that someone could visit us mostly in real time, right? When we think of long-term space travel, so far we always felt like, well, the time horizons are so far off. We know this from light, that by the time the light gets here from a few million light years away, a million years have passed from the source where we actually got the light from. So I guess so far we always felt, well, the time horizon might be so different, right? We track aliens maybe relatively useful in a useful way for 200 years or 300 years or maybe 1,000 years or 2,000 years, but that's about it, right? So, but the time horizon just for interstellar travel could be so easily just off by a few million years that it would be very easy to miss that life that now finally can track aliens. And that seemed to be a very convenient way to get out of the Fermi paradox. But with the warp drive, you don't have this excuse anymore, right? Because it would be real time, so to speak.
Well, you could. I mean, you still have
that problem because it leads me to this question: Do you feel time in the universe? It is the same for everyone involved. Like, is it necessarily the same, or do you think that's what we think right now? But this concept will change over time. Well, maybe that's too much time in one sentence.
Yeah, there's a lot of different times in there. Um, well, so yeah, this is something that I've thought about on and off. As a fan of science fiction, as somebody who likes to think about these different possibilities. So I would say regarding things like the Fermi paradox and why we haven't already made contact, or will we ever make contact if we ourselves manage to become this starfaring species. Um, my current thought is that it is very difficult to get to this point. It is very difficult to. There are a lot of pitfalls in evolving technology and society in a way that is sustainable, that can be that is long term, that won't necessarily collapse at some point and necessarily have to start over, or worse, the species that was responsible for it no longer exists, right? Or that they can't repeat so that they can't repeat this building process technologically speaking. I wouldn't be surprised if life does exist in such quantities that one might believe from the Drake equation, or versions of the Drake equation, that these barriers um, may be very high to moving to a point where you can observe, say via telescopes or whatnot, other civilizations, even though you're still bounded by the speed of light, uh, and and then transfer from there into a spacefaring civilization. I think that is a relatively large barrier. You have a lot of different technological advancements that need to happen in a way that doesn't necessarily prove catastrophic for the species, such as nuclear power. Right? Nuclear power can be a wonderful tool, but it can also be very destructive. Um, so it may prove to be the key to interstellar travel, even if it starts off being in a subluminal sense using one of these projects like Project Orion, where you have essentially a very large nuclear rocket moving at some tens of percent of the speed of light to nearby stars. Or if we can maybe create a warp drive that is powered or finds its source of power from a fusion reaction, just a very efficient one and a very efficient warp drive. Um, that that the society that builds this and is able to advance this and facilitate all this has to also survive alongside, right? You need to be able to cultivate the people, or equivalent of people, whatever these alien civilizations look like, that can make these advancements in understanding and advancements in instrumentalities and advancements in the
But
various
the but
technologies
Eric,
that end up being
as
used.
yeah, but Eric, as you know, there's just so many planets, and we know that the basic ingredients for life are everywhere. We have. I think there was bacteria on Mars. I'm not sure if that's really true, but there was suspicion, and there was water. So the basic ingredients for life, and their carbon atoms, they're all over the place. And yes, I mean,
Mm-hmm.
I agree with you that there's a civilizational challenge, which comes with consciousness, especially, right? This upgrade to life, which is still a perplexing question to me. Why only one part of the primates got it, and no one else in the animal universe can ever catch up to it? Seems really odd to me. But let's assume this is the way, and I mean that this is eventually coming out everywhere. But the survival, the basic mechanisms of the universe seem to be relatively simple in that sense. There's an abundance of energy, and there's an abundance of probability that there must be more out there. And yes, I agree. I mean, there's always challenges. But from my point of view, and correct me if that's wrong, I know I get a lot of flack for this, is we seem to be headed somewhere. Like we're definitely working against entropy. It's more complicated what we build. It's more universe shattering by the day. Nuclear power is the latest to it, but there's going to be way more
Mm-hmm.
technology. And I feel we're headed somewhere. And people say, well, it's like the ants on one side of the room, they come to the other side. It doesn't mean it's headed somewhere. Yes, but I mean, we're talking about moving space around so we can travel theoretically only, but maybe practical in
Yeah.
500 years, 10,000 years, whatever the number. This is, I feel we're definitely, someone put us up to this challenge. It's not randomness to me, but that might be because I'm part of it, right? Because I'm biased. But it just seems so strange that you compare this to ants on one side of the room making it to the other. They're not had it anywhere. It's random. Maybe not. It's just this feel. It's not a good analogy for me.
Yeah, I mean, what compels us? Because you're talking to somebody who, for some reason, felt compelled to try and make one of these, earth-shattering inventions, theoretically. But
Yeah.
I
You're a real
definitely.
pioneer, Erik. You're a real pioneer. You have to
I
build it in your mind first, right? And
I
then it
feel
might become
right. We right. We have to feel that we can be audacious enough to try these things, and definitely some of us do feel that way. Enough of us, certainly. Although I do question that sometimes. What that I'm on the right track or the like. But I definitely do feel compelled to try new things. And is this purely an evolutionary byproduct? Right? Is this something that is just me or our species trying to better and perpetuate itself just purely from a fitness perspective? Or is there something deeper going on?
Yeah.
That is a question I do not feel qualified to answer. All I know is that I do definitely feel compelled to make to make these improvements, to be able to facilitate humanity to be able to reach further than it's been able to before in this one small way.
But
I
don't you
definitely do feel
like
that compulsion, but
it's a gut feeling, and it's a gut feeling. When I want to talk about it, I feel like, and it just goes back to what Newton always has been saying. It's when you look at the universe, doesn't it feel like there is a creator? Doesn't it feel like someone created this as a simulation? You could say that, or created it as an environment to test a theory or to build. I always feel the Big Bang is such a bad excuse. We're like, okay, we can't talk about it because we can't see it, and there's a Big Bang, and really, that's it. I mean, shouldn't we really at least speculate about, is there a reasoning that someone put us up to this challenge, and we are like this child that now grows up, and there might be other children across the universe? That's how this seems to me. But obviously, that's a gut feeling, right? This is very difficult to ever prove with scientific theory. But it seems to me much more likely that it's all just random, and the Big Bang was this random event in the universe, never happened before, can never happen again, and it will eventually deflate back to the Big Bang. It's all a little intentionally blindfolded.
Yeah, this conversation surrounding simulation, I find very interesting. How it starts off in a very technical viewpoint, but then almost takes on a spiritual nature in the end, almost a religious context in the end. Very interesting how that has evolved, that conversation. But in terms of the philosophical conversation around the origin of the universe, I think it. How do I say this?
Well, do you feel there's only one universe, or there's more than one? And that's a quantum mechanical actual theory that's being discussed. So there's for every single decision you make, there is another universe.
Many worlds. Well, I think there's a lot to still be explored in the origins of quantum mechanics. I think many worlds is one. It's you very quickly, if you think about many worlds, and especially if you fold in string theory to that you have every available type of physics present in the universe. By universe, I mean all of reality, even those parts that we can't see, that have fallen out of causal contact with us, or were never in causal contact with us, really, but express physics a little bit differently and may or may not contain life, so that really all possibilities are presented, or a simulation that some entity has fine-tuned this universe to create life, possibly, or for some reason that is beyond our comprehension. or it's also possible that our conception of quantum mechanics is still very new, very imperfect. That we don't necessarily have enough of the pieces together to understand exactly where quantum physics fits into how our universe operates, right? And because of that, I somewhat defer these conversations a little bit. I think there's a lot more to be done without necessarily appealing to anthropic reasoning at this point. So, because you could say, yes, the universe is the way it is because otherwise we wouldn't be here to observe it.
Yeah.
The parameters are sensitive enough that if they were much different, then poof, you and I wouldn't be talking. That is one possibility, and I suppose it'll always be there. But I think there's, I think I'm not completely satisfied with it.
Yeah.
I think there's, there are other possibilities, theoretical possibilities that I think should be explored before we, in my mind, throw up our hands and say it had to be this way, or we wouldn't necessarily be here.
Yeah.
And I take a similar perspective on the simulation conversation. It's quite possibly true, but there's only so much one can do about that once one accepts that, unless one then changes the conversation of I want to understand the universe, or I want to understand the mind of the creator of that simulation, or
yes,
however you want to phrase what we are currently living in.
I mean, it's certainly just you just transfer every physicist, I think, wants to actually learn about the nature of the universe, at least an astrophysicist, and that's kind of an origin motivation, an original motivation. And if these rules of the universe, are they following someone's purpose, someone's plan, or is they all random? Well, that's certainly, you can debate about this, and I think it's very popular right now to say, well, there cannot be a creator, or if there one, I don't want to know about it. But I think I always feel like isn't there a little bit of a utility discussion missing, right? So yes, the universe might be just this quantum computer that's all random, and we're like this part of a cloud. We're like in a big server rack, and we just don't know it, right? It could be. We are basically in a rack space of the universe, but maybe this thing's got to have a purpose, right? I always feel like it's very rare to come across something in life you don't know. Well, none of us knows the purpose, but it has a purpose, and this purpose is often, well, it's boxed into higher order purposes. Let's put it this way. So there's a huge hierarchy of purposes sitting on top of pretty much anything that exists in life, because usually it gets outcompeted or forgotten. Well, from my point of view, I always feel there is some hierarchy of purposes out there, and that seems to be there's a utility, right? Something has to be worthwhile to be existing, and that discussion never enters. I feel the modern discussion about the universe from a I'd say hardcore scientific standpoint, but that would be awesome, because I think it would make speculating and coming up with new theories so much easier. Or am I seeing this all wrong?
Well, I think kind of in the undercurrent of what you just said is this concept of, when you're talking about worth and whatnot, there's really still a very human context to that. Worth it from a human perspective. I mean, how do we conceive of worth apart from ourselves? That's a much more difficult question. From within our society or within ourselves, it's much easier. Well, much easier. We can also get very philosophical about that as well.
No, but I mean, what is the reason of time? Well, why do we have time? I don't want to say this is something that has to be working on Earth. That's silly. But why do we have gravity and gravitational waves? Why? I mean, are they just there for what? So I think this discussion is useful. Obviously, yes, we cannot just judge by the order of our current planet Earth. That's a little silly. it's a tricky question. We're definitely
It is a tricky question, and oftentimes we come upon these phenomena like a gravitational wave or whatnot as a byproduct of our attempt to understand the universe. Right? Gravitational waves weren't necessarily the impetus for forming the general theory of relativity. They were a result of it. Right? The initial attempt was to fold in gravity to this concept of the relativity principle. And then some years after, well, not many years after, really, I think it was only a handful, that the concept of that you'd have this self-propagating radiation type solution in the form of these two polarizations of gravitational waves, analogous to what you would see with the electromagnetic field in light, that you would also see this. And just trying to keep it close to human concept of human concept of meaningfulness. We seem to oftentimes pursue physical theories, let's say within the 20th century, based on some sort of need for an explanation. There was some phenomena that we didn't necessarily understand, and we needed something to fill in the gap. And there are a number of different approaches to do that: top down, bottom up type of approaches. Just filling it in. A common one that's still fairly popular today: there's a phenomena you don't understand. It's a particle. Make a particle out of it.
I thought you would say God. Usually God is, when we don't know the answer, we say God. And that worked for us beautifully, right? But I think this is not what people dismiss religion with this. It does that 100%, but it's not.
Well, it's kind of been replaced. It's kind of been replaced as our understanding of the universe has become more technical. Is that explanation, that this appealing of a certain type of explanation? It's a particle. Anthropic reasoning. We're just in a simulation. It seems like we're oftentimes substituting one default explanation for another, and we've managed to stumble through and seemingly make progress. By progress, I mean able to come up with technical explanations that fit the data and seem reproducible, and also fit new phenomena to a degree, until we find another phenomena that evades us for that moment. But the reasoning just seems to be largely. There are people who definitely go a different route. They will appeal to some other type of reasoning. Elegance is a popular one. How successful that's been is another conversation. But but go ahead.
Yeah. Erik, while I have you here, one of these things that we are all so super curious about is things that go faster than the speed of light, because since Einstein we have this speed break, right? Everything is suddenly so slow that we can't really experience the universe at all. And we just talked about your theory of creating a warp drive and how this could work. What else is out there where we know that's faster than the speed of light, where we are pretty confident, okay, this goes beyond the speed of light, and we might be able to either use it for transmitting information, or for travel one day, or just to see the end of the universe?
Right. So there are a couple phenomena, again, those that we don't completely understand, that seem to have properties that are superluminal or non-local. Dark energy appears to be one of those, right? It seems to have properties, at least as near as we can tell, that aren't necessarily entirely local. The types of interactions and whatnot, or the very fact that it induces this very global phenomenon of inflation on the universe, has that sort of impact. Another common one, which is maybe what you're getting at, is this concept in quantum mechanics of entanglement. Various non-local qualities of interaction or non-interaction, really, of constraint within particle physics. This is something that I've thought about some, and maybe picked up on from some of my previous research with dark matter. Is that we have this concept of a non-local interaction, or not? Sorry, I keep calling it interaction. We have of non-local phenomena within particle physics due to how identical particles, from a quantum perspective, how they interact with one another and how they can become correlated over very vast distances due to their statistics. How this could possibly be used for something like communication is not well understood. In fact, many people believe that it cannot. That either by some arguments of relativity, that you aren't actually transmitting. Well, some arguments of information there, you aren't actually transmitting information. Say if you have the classical Bell spins example, where you have some quantity of known spin, or some particle of known spin, say spin 0, and it's a massive particle that decays into two smaller particles with entangled spin. So say one has spin up in some orientation, the other one would necessarily have to have spin down to conserve total angular momentum. And then these two particles, because they have excess energy, propagate away from each other very quickly. Not necessarily faster than the speed of light, but say you have a detector at one of the ends of some experimental hallway, and you want to detect what the spin is. Once you detect the spin, once you specify the spin of one of those decay products, you know what the other spin is. But did you actually transmit information? Could you actually manipulate the spin? Or did you merely detect the spin? The difference between transmitting information and using this non-local effect, or it just being a purely observational non-local effect, really seems to rest with, can you dictate what spin it had? Because if you can, if you can say, okay, I'm going to make sure the spin of this byproduct is up, the other one is down, and if you can make the next one down, up, 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 down, you can then start to transmit information to the other end of this hallway in a way that is necessarily subluminal or superluminal, even though the original products of this decay never propagated away from each other faster than the speed of light.
Yeah. So I'm not sure if I don't really know the terms well, but I think the example is always made, and you just condense it to a hallway. But the example is made that there's a particle. Once these particles are entangled, once it changes on one side of the universe, on the other side of the universe, it would change immediately. Would change as well in the same split second, or the same moment. Obviously, the observation is a whole other problem. Once we observe one, we interact with two particles. So we only observe one, but we actually change two particles on two sides of the universe. That seems really stunning. Is that still true, or is that physics doesn't necessarily believe that's what's happening?
Well, there still is. So, yeah. Simple answer is that there's still an element of that which is true.
Okay.
The challenge is, and where things get a little bit messy, is, can you do anything with it? Is there utility to it? Yeah. From an information theory perspective, or from a transmission of information perspective.
Yeah.
That I believe the majority would say no. There's still some people who think that it's possible, but is there some significance to this effect from a purely physics perspective, as opposed to from an engineering perspective? I would say yes. And I've done a little bit of thinking of this with respect to dark matter, and if your dark matter necessarily is this highly correlated fluid, what would that mean for the structure of the universe, or structure, say, of our galaxy? but that's a bit different than necessarily transmitting information from one end of the galaxy to the other. You need to have that level of control over what one of the particles on one side was doing, and such that you could effectively not just know what the particle on the other side is doing, but also transmit a message to whomever might be observing that other particle.
Yeah. Understood. It just seems such a hopeful message that this is so cool, right? Because Einstein, as much as he's a genius, he kind of is a big downer, right? Maybe you can help me understand the concept of dark matter a little better, right? You just referred to it as dark energy, dark matter. What do we know about it? Is that something that is we can't see it, and is it something that is really inside our universe, or we feel like, well, what do we know about it, and how does it actually work? And is it bound by the same relativity concept that we know from light?
Let's see. So yeah, the concepts of dark energy and dark matter. You can consider the term dark maybe not to be as much of a technical term as maybe just insight into our knowledge of these things. Dark as in we don't really know much. We're in the dark on these. Yeah. But this is kind of in the vein of make a particle out of it. Not quite to that extent, but similar to, in terms of phenomena that we seem to observe but don't entirely understand. And this is our way of trying to reconcile observations with our understanding. So the observations actually for dark matter occurred first. So back in the 1930s, there were a number of observations of, at first, galaxy clusters. So the hierarchy of structure in our universe extends, from gaseous nebulas, solar systems, entire galaxies, and then collections of galaxies. These are the structures that we can see. Collections of galaxies, and also voids in between galaxies that can also be quite voluminous. And so in the 1930s, these clusters of galaxies were observed for their kinematical properties. How fast are they moving relative to each other, to try and determine, say, how massive one of these clusters would be. And it was found, and this research was done initially by Fred Zwicky and his collaborators, that the amount of mass that would be necessary to keep one of these bodies virially bound, or essentially bound by its own gravity, was approximately 100 times or more greater than the amount of mass that you would estimate based on the amount of light that was given off by each of these galaxies and mapped to a certain mass. So if a certain galaxy was so bright, there was this little table that you could look up. Okay, it's or a graph you could look up, and it's this galaxy would be 10 to the 9 solar masses. Yeah. Based on the total number of stars it was thought that would make up that galaxy. But there was this huge disconnect between how much mass you could see and how much mass you couldn't. This mass appeared to be dark, or not just dark, but invisible, perhaps, right? Depending on your precise model. It's possible that you could actually see through it, depending on what it was made out of. And so these observations then extended from clusters of galaxies down in scale to individual galaxies with these famous rotation curves, that if you were to take the total mass that you'd observe in a galaxy like Andromeda, and you were to map out that mass density from the visible matter, and just according to that, plot the rotation curve that you would expect from that matter of a fictitious body rotating around that center, you'd expect, because the galaxies are very centrally dense and very compact, that you'd have this curve that would go up to some maximum value and then drop back down to zero. So the stars on the edge of the galaxy would be rotating very slowly, which you could also observe via Doppler shifts, relativistic effect, how fast these bodies are actually moving, and the actual rotation curve had this initial increase towards the center, but then it flattened out and stayed relatively constant quite far out, indicating that either our concept of gravity was incorrect on these scales, or there was some other material present in that galaxy that was also gravitating and creating a more intense gravitational field within the galaxy, and especially out in these outer reaches of the galaxy, that required these bodies to move that much faster in order to maintain their radial displacement from the center of the galaxy. And there's been a lot of other mounting evidence about why we think that there's something either wrong with gravity, or there's another form of matter present in the universe that we cannot see. Similarly, with dark energy, we have this acceleration, and we believe that there might be some media present in the universe with very different properties from matter that's causing this inflation type behavior in our universe today. But focusing in on dark matter, having these possible options of something wrong with our theory of gravity, or some new material present, a lot of focus has actually gone on there's some new material present that we don't necessarily understand. What could it be? And there have been many, many theories put out, ranging from it's a new fundamental particle to it's a bunch of black holes that are individually very small, but they are so numerous that we can't really see them. They don't necessarily have large accretion disks that are radiating that we could see surrounding them. The research that I've done has been more on there's a new fundamental particle in the physics of our universe that we have yet to observe, but can exhibit these properties. And more specifically than that, I've been thinking about the axion. Yeah. The axion's a very particular one. You had a question?
Yeah, no. I'm just listening. I don't know enough about it. I know what I was hoping for, and obviously you already indicated that this is all just work in progress. What I was hoping for is that a lot of this dark matter, if it exists, might be not bound by light, right? So in the sense of it doesn't. It gives us a way out of this speed break, but that might be or might not be the matter. We just don't know enough about it, right?
Well, as far as a possible new source of media that would have exotic properties that could possibly get us beyond the speed of light barrier based purely on its properties, on the material properties of that one source, it would most likely be with dark energy. If dark energy actually does turn out to be some new fundamental field in physics, a physical field, as opposed to a field of study. Of course, it would be a field of study if we.
Yeah. Do we see it also in our galaxy, or is that something we only see from afar?
Well, so dark energy, in order to have the properties to imbue our current universe with the properties we think it does, would have to be very diffuse. In fact, it wouldn't it would interact. It would gravitationally interact with itself, but the way it would interact is very different from how we would think about matter. If we have matter, it's attracted to other matter, right? You'd expect it to collapse locally. It turns out that this dark energy, any perturbations in it that might cause it to collapse, if it had some nice classical mass and it had some Lagrangian that very much looked like standard matter, it does not appear to act that way. It appears that if you were to give various perturbations to whatever the dark energy field is, that these perturbations would dissipate. They would be repelled from the regions of higher energy density in the dark energy field would dissipate. They would all flatten out, and we'd have this very diffuse field throughout the visible universe. And so To answer your question, our current concept of what a dark energy physical field would look like is that it would be present everywhere, throughout the Earth. It would just be very, very weak. And only on the largest scales of the universe would we be able to see its effect. Because gravity being a scale-free force, meaning that it acts equally strongly at all distances, or it has this nice inverse square law as far as the gravitational acceleration field is concerned. That all the other forces would dissipate in intensity, but this one field, at the largest scales in our universe, gravity seems to dominate, and so that's why a field that is nearly homogeneous across the entire universe would dominate the physics on those length scales.
Yeah, understood. Okay.
Mm-hmm. But so that would be the one that I would think possibly would have properties that would be inherently non-local, that would maybe give us some insight into physics that could transmit information faster than speed light, possibly. Right? We still know very, very little about it, that this may not be the case at all. Dark matter seems to be, if it is, in fact, a matter-like field, a fundamental field, it behaves very much like standard matter that we've encountered before, in that it, if you were to expand say a box, say if you take a cosmological box of this dark matter, and there was so much inside at one time, at some time t1, and via the expansion of the universe, the box would grow in physical size at some time t2, the total amount of matter in that box would stay the same, but the density would scale down as 1 over the volume, the three-dimensional volume. That might seem relatively a benign statement, but not everything necessarily behaves like that. Light doesn't behave like that, right? Because if you were to have so much energy density in light and then expand it, not only do you have the same number, say you'd have the same number of photons inside that box, but the wavelength of the individual photons would increase with the size of the box. So the energy of the individual photons would go down, meaning that the total energy inside that box would decrease. And the energy density would decrease faster than with matter. Dark matter, as well as we know it, scales more like the former. So it seems to behave much like a standard matter field, particularly when we also look at how it forms structure in the universe. It seems to collapse very similarly to matter. In fact, it's almost the ideal type of matter because it doesn't have all these other interactions, say with photons, and it's not giving off a lot of heat or radiation. It's a really well conserved interaction, which means it's not going the disturbances in the dark matter field, when they collapse, they're not going to collapse as tightly as the matter that you and I are made out of. Right? The you and I are made out of is very sticky. It sticks to itself. It really allows for a very tight collapse, which is why the distribution of matter, the baryonic matter stuff that you and I are made out of, in, say, simulations of structure formation, indicate that the galaxies are going to collapse to be much smaller than the surrounding halo of dark matter. The halos of dark matter, which are what we call essentially the galaxy analog in the dark matter world, are going to be much bigger than the visible galaxies, which explains those rotation curves. Because even though there's dark matter all throughout the visible part of our galaxy, if this model holds, the distribution of the matter in the dark matter in its halo is going to extend far beyond our farthest star in our galaxy. And so it's going to look like, from the perspective on the scale of our own galaxy, it's going to look like there's just some continuing distribution of matter that just goes on forever, which is going to create this flat rotation curve for our stars.
Yeah. Well, a lot of people, I don't know how scientific this is. A lot of people who are on psychedelic drugs, they typically make that assertion, and we'll get to the dark matter there. They make this assertion that we are we are restricted in our current, three-dimensional plus time world. And once you're on this trip, a lot of people come back and, it's just a few milligrams of active ingredients. Many people will come back, I'd say 50%, say, well, there is another multidimensional space. So there is something that is in the same space as we are, right? But it's basically in a dimension that we cannot penetrate, that we cannot view, kind of like dark matter a little bit, right? Obviously, we're talking about slightly more, very different concepts.
Things beyond our perception.
Right.
Our normal perception.
They could be, it's very Huxley, they could be, like a dark matter. There is something else out there, but it's the aliens are already, they're here already, right? But they're in a different dimension. That dimension very weakly interacts with what we are seeing. But it is the core concept, and I think this is where people are going with this, is not that we are actually, that the time and space and what we are preserving, that's just one random dimension that we are, for whatever reason, we chose to see. It's actually consciousness that makes the universe. And there is this argument that goes a little further, is that without consciousness, without anyone who can feel time like we can do it, like animals, we have the impression they can't feel time. They live in it, but they can't feel it. So without consciousness, it's the singular property that we humans have, which is really strange. If you define it relatively narrow, you can always go further with this. But what a lot of people make that claim, I don't know how scientific that is, that that consciousness is that core concept of the universe. And these other dimensions, they're hidden from us, but they're there. And if we could access them, then we would see the real universe, so to speak, right? That's kind of how this is strung along. I don't know what you think about that.
There's a lot to try to unpack there. Maybe I'll ask you a question. Okay, so what constitutes consciousness? Is it human consciousness, or is there some ubiquitous consciousness that we're talking about?
That's a very good question. I would define it as something where you can feel time is passing. So it's a concept where you realize, well, there is a past, there's a future. It's kind of what we do. We build the simulations and figure out, okay, what are we going to do next and what is our goal? This you don't see in the animal world as much. We call them instincts, and they can't at least express their version of the future. We can, right? And we've learned how to do this, which seems pretty singular. But that's kind of my understanding. The concept, you can obviously define it bigger and can say, well, anything that could be conscious and has any point in time. But I feel it's more of an experience, right? So what I find so stunning is that without anyone with a consciousness, time doesn't really exist. I mean, to the planets, does time really exist without the observer who's conscious? I don't actually know how to answer this.
Yeah, I would have some difficulty answering it as well. So I would say that, humans seem to be unique on our planet in terms of the ability to plan, the ability to have a sort of coherence time to our concept of reality. It allows us to make plans and see the results thereof and make adjustments based on that. But there are limitations to that. I mean, our ability to record with high fidelity, with even longer time coherence than, say, our memory, has shown us that our memory is not necessarily perfect. So I would have some questions about what exactly we mean by our concept of the passage of time, because the way I think about it has to do with, in terms of accessing the past, has to do with memory, or how we store previous experience. And we found a number of ways to do that, right? Thousands, many years ago, before reading and writing and YouTube, we had, our own local drives to store this on. And it did fairly well. We came up with many different ways to improve on our memory. songs and things like that in order to improve the coherence time, even many times across generations um, of the past and of information. Um, but and we definitely have this ability to abstract to imagine what the future will be. But I don't know about you, but I imagine all sorts of different possibilities in the future, and most of them never happen. I'm wrong most of the time, right?
Yeah.
You find that with research, you think, oh man, I've got this great idea for a warp drive, and it's going to work like this, and it's going to require this much energy, and it's going to go this fast, and it's going to require matter with such and such properties that are going to all work out. And then you try it, and either just by pen and paper via the mathematics, the underlying mathematics, and it doesn't work. And then you try something else and it doesn't work again, but eventually maybe something does work, but it wasn't necessarily the original concept. So we can't perfectly predict the future. We can't. We're becoming better at remembering the past. But in terms of this some idea of underlying consciousness, encoding the concept of time. It
Well, it
would
goes
have to be
back to the
something.
simulation argument, right? It's kind of, it's like,
It does.
with,
It does.
it seems
It does.
all so weirdly aligned, right? You can only consciousness can really find time as they're really intensely connected. Whatever the real connection is, and then the speed of light. You will probably say, well,
Right.
that's another very human-centric approach, but that's a lot of coincidences that I see there, and they only happen at the last whatever 40, 50,000
You mean
years.
the constraint of the speed of light?
Yeah, well, it
Okay.
goes a long time, right? So light and time are so the speed of light and time are so intertangled.
In our current concept of the universe, yeah, but it's also possible that just as 100 years ago we didn't necessarily see that connection, it may be that may not be the complete connection. There may be something even more fundamental to our concept that we can, well, I hope, because I oftentimes have an easier way of understanding it if there's some technical explanation, if there's some way that you can precisely express, oftentimes via math, how a mechanism for how the universe operates that's more accurate than what we have. Because it may be that, right, this concept of space and time, they're all just very nice markers that allow us to conceptualize, that they're really just abstractions of human beings to make order of chaos, right? Even these concepts, these words that are coming out of my mouth are examples of that, right? The concept of chaos. But yeah, this has gotten us very far, just like the various other ways that we stumble around to try and understand the universe. But is something closer, is something more accurate, this concept of consciousness, of some ubiquitous consciousness via a simulation or some other system. That's a good question. I'm
not smart enough to understand it, but I feel like there is too many coincidences in our current theory. I mean, it's too. The pieces fall too much into place, and I think there's something else out there. But again, I don't know the answer to it, so I can only answer the question. I'm definitely not smart enough to understand it and come up with a unifying theory. I think that's because of quantum theory and the esoterics that it introduces to this nice, neat model. I think people are longing for this, and a lot of people have been working on this and made good progress. But so far, we have nothing that gives us new predictions. Right? This is what a model needs. It makes better predictions than the old one, at least in one subset of predictions, right? It's like Newtonian mechanics. It will not replace it. It will just go into a different sphere and work
right.
better in a
It'll
new sphere.
have a larger context or whatever the case may be.
Yeah, galaxy-wide travel. That's what we want to know. That's hopefully your next white paper. How do we jump to the next galaxy?
Yeah, well, I don't know. At this point, I just want to see if I can build one of these things even in small scale.
Yes,
build up to it.
Do you think that's possible? Can you running some experiments? Do you think that's doable at all?
Well, I think still there's an amount of theoretical work that needs to be done first. Like, as I've mentioned throughout the conversation, a need to nail down a mechanism for creating and accelerating one of these things. Right.
Yeah.
Right now, all of them have just existed. Right. The way that they've been presented is that they existed ad infinitum. They've always been there. They will always be there. But that's not really physical and not very helpful from an experimental point of view. But if you can find a mechanism to create one of these things, and if you can find a way to make it energetically efficient enough that you could create one in a lab strong enough to be detected by some instrument, then we have the makings of an experimental verification. But those two elements need to be completed first, which are things that are very much on my mind right now, because I would like to see this. I would like to see experimental verification or evidence that the path that I'm on is faulty for some reason. That maybe I'm mistaken.
No, you got to call up Robert Zubrin. He's been writing the book The Case for Space, and he's been working on ways how we can actually get anywhere in the solar system and beyond. And he needs details at what we need to do this. And he would love to. I think he would love that theory, and would probably give a lot to make it happen.
Oh, okay. Well,
I'll put you two in touch. Let's see what happens.
Excellent. Yeah. Wonderful. Yeah, I would. At the very least, it would be a very exciting conversation.
Yeah, I think so too.
But I would very much like to see that happen. Yeah.
Same here. Thanks for this update. I hope it's going to work out, and in a couple of years you come back and you say, well, we just built this thing, and why don't you try it out? That would be my hope. Erik, thank you so much for taking the time. That was awesome. Thanks for all the insight.
Yeah. Thanks again for the invitation. It was a very interesting, exciting conversation. I was glad we were able to make it happen.
Thank you. And looking forward to next time. Erik, take it easy.
Yes.
Bye-bye.
You too. Bye.
Talk soon. Bye-bye.